Okay, so what I want to do is I think the magnet is attracting the metal in the folding table there. So I'm just gonna switch it over so let's see how smooth it really would spin. Okay, so what I want to do now is to measure what kind of voltage I'm going to have through this coil. So I'm going to get this, and I'm going to connect this into the device over here. So I'm going to go ahead and move this out the side. Also need some more tape down here, obviously. So I'm going to go ahead and do some more of that tape. I'm going to go ahead and get the squirter. See if that's just because it's which way does it want to go? It's just the artifact of the snare. Okay, so anyway, let's go ahead and connect this to the ends. Let's use a better connector. Extra leads. Where are the extra leads? That's not the one. Where are you? Where's the original? Okay. It's not quite what we'd be looking for. But this should work here. And these should work if they're long enough. Okay. And so let's take a more ground level view of this. Maybe we should have had that view all that time. Nah. Alright. Okay, so let's go ahead and take a view of this. And this one here. Alligator clips would be easier. No, this one. It's too short. Seriously. Okay, so I'm going to remove this here. So this is the only other one I've got right now. Let's use these. Let's use these. I'm not sure what happened to the other cover for this thing, but whatever. This over here. It's a COM port here. Get some more leads from Fry's later on or something. So being able to measure resistance. We're just making sure if connected to the right coil. Okay, so this is showing you, according to the accuracy of this meter, the resistance of one of the S.H.O coils. And now what I want to do is show you that this will produce alternating current, or alternating voltage here. So at that speed here, 1, 2, gives you a good idea of what kind of voltage we've got. So at this speed, it's inducing very low voltages. Here's a 0.1 of a volt. Thereabouts, let's go ahead. So it's very low voltage here, 0.1 volts. We're going to alternating instead of DC voltage. So it would seem to be able to generate 0.1 volts. If it's running at, say, 60 revolutions a minute. Anyway. Okay, so let's go ahead and check this out here. Positive voltage, negative voltage. Positive voltage, negative voltage, positive voltage, negative voltage. Make sure that this stays where it's supposed to. Right? So I think I'm going to leave it like it is right now. I need to study the amount of voltage a bit more that's being generated in this unit. And trying to anticipate what the performance characteristics would be. All right. So here. So I'd like to thank you for your time. Let's go ahead and look out around here. I don't think I'll be able to finish the show drive before it deletes this up, so I'll be shooting video elsewhere at some point. Okay, all right. Let's see what time it is now. And why is that still giving a reading here? That's weird. That doesn't make any sense. You know, I'm gonna hook up an oscilloscope to this. I got an oscilloscope, a little miniature oscilloscope, and I could actually see if maybe this will pick up something better. Oscilloscope. Something else that goes with this. Small containers. Seed Studio. Where are you? Supposed to have smaller containers somewhere. So, where are you? Here it is. Okay, so these are just little probes here. That doesn't really make sense. I don't know why that's still giving a reading. Probably also have to do some WD-40 in the bearings so they can run smoother. Just barely. Volt division. Okay, so let me go ahead and have you zoom into this. The S.H.O Nano thing. Alright, so basically I've got it at the vertical setting is at 0.5 volts each division. And so when I actually rotate this, you see, wait a second. Oh, it's not connected, no wonder. Let me go ahead and connect it again. So if I were to do this, you'll see that this will pick it up as around 0.4, 0.5 volts up and down. So if it goes up one division, oh wait, my hand's too high. So if it goes up one division, that is 0.5 volts. And if it goes down one division, it's negative 0.5 volts. So anyways, so I'll actually have to put some glue on the hex nuts at some point. I don't think I'm going to do it tonight, but apparently the RMS multimeter cannot pick up what I'm seeing here. It's like the voltages I was looking at, I was seeing there was really low, and it didn't make sense that it would be like 0.1 volts, and I knew it was going to be more than that. And so when I saw, when I see this one, I see it's actually, it makes actual sense. And at least at this speed, it's and this is just with one coil. It's about 0.4 volts up and down. So with two coils, of course, we would get more than that. And of course, it's like a sinusoidal thing, kind of. Let me go ahead and look at. Time base and time base is one thing. Let's go ahead and increase the So now I made the division point. Let's zoom out. This is a little too close. All right. So over here, the divisions are 0.1 volts each. A vertical. That's the vertical divisions here. And so this is the center line. And keep in mind, it's just one S.H.O coil, so that's kind of, it's going to look kind of asymmetric. Yeah, now I'm looking at the screen just to make sure that you can see it. Cool. So, one thing I could do, let's go ahead and connect this thing down to there so we can get a better idea of what's going on. So what we have to do, I'm going to have to strip some of this wire here. And let's go ahead and do that. This is also a 12 gauge wire, and I'll be connecting one part of the coil to another. Okay, so this is pretty much along the length I want. So I'm going to go ahead and cut this. Okay, and so it's there. Kind of give it like this bend here so we can connect two terminals. Down there. And so I need to strip this wire. It's 12 gauge solid. So I'm going to go ahead and grab this here and strip it out. Really easy. Other side's the same way. Okay. So there it is. Now I need to do crimp connections on here. I cut a bit much on each side, so what I'm going to do is I'm going to trim this here just okay, there we go. And then over here as well. That's too much. Oops. Focus. 12. Come on, 12. Come on. Okay. So now I'm gonna have to crimp it. Over here. And so come on. Okay. Hold. So that one's taken care of, and then the other side is done too. Okay. Need to do some more here. Oh, come on. Okay, that's terrible. We're not. I think that took care of it, actually. Okay. Let's roll this. But this has to be redone, removed. Okay. Let's try that. Okay, not too much. Should be good. Solid. Okay, so now just want to connect these together. So I have to screw some of these things on here. So here it is. Got some of this over here. These screws and nuts. See, it's been 6.5 hours. Go ahead and get some of these out. And let's connect this one here. Go ahead and put this here. So those two ends are connected, and so let's go ahead and measure the inductance of this. With both coils connected. Okay, so let me go ahead and put the rest of this back in here. Get little scratches. Okay, what else? Just had a rubber band. This is a big one. A twist tie. I had a twist tie. And where are those prongs? The right prongs. Or we could just use the, no, this is too short. I have a little multimeter, don't I? So the multimeter should be in here. Okay, where is the multimeter? Oh, there it is, on the windowsill. measure the inductance of this. Oh, now you're doing that again. Let's pull it on the board. It's not good. Remove cords and everything. Oh dear. Is this really not working anymore? Ah, jeez. Alright. These are not durable. Oh, well, no wonder it doesn't give a reading. I have to connect it. Duh. It's connected. Okay, so with this reading, we're getting 0.95 millihenries, and that's 950 microhenries. Let's go look at a different resolution of the reading. This gives us 0.938 millihenries, or 938 microhenries of inductance. So, alright. That's with both coils connected in series, with the current coming out of this direction and then going back in, or vice versa. So they're essentially connected. So now that I've connected, I can now go ahead and see what kind of voltage I'll have on the oscilloscope when I do this. So I go ahead and let's remove these. I need to get a better alligator clip thing for this. So this is kind of, let's see. Let's hook this up, and over here, let's hook this up. So that's what we do. And we need reading for this. All right. Okay, so I'm going to go ahead and remove the memory thing here. Oops. Okay. Okay, good. Off. Alright, so I've got the wire hooked up to this, and I should get a reading. Now, right now it's at so it's 1 volt divisions for the vertical axis, and so you can see that as it is right now, I'm having it going at positive 7 volts to negative 7 volts back and forth as fast. So I'm spinning it. Alright, so I'm able to get, with the spin rate I have here, about about 1 volt going in each way, just by hand spinning it. Now keep in mind the resistance of the coil let's go ahead and measure the resistance of the total coil. It should be about 300 something milliohms. So let's go ahead and measure that with our milliohm meter. So if you think about it, you get you're getting like a plus or minus 1 volt through 300 milliohms. That's, you know, you're getting over 3 amps already. And because each coil's got 25 turns, that 3 amps times the number of turns, so I have, well, it's 3 1/3, but whatever. If I multiply 3 amps by 50 turns, then that's 150 amp turns. So there should be ample amount of current going through as far as the induction goes. So let's go ahead and the reason why there's no current going through now, of course, is when you hook up and try to take a resistance measurement, or let's say you're taking a voltage measurement. It's going to measure the voltage across a resistor, and that resistor's got much more impedance than this, so obviously there's not much current when you're using the little oscilloscope. So anyway, this milliohm meter should give us a reading as well, as far as this goes. Oh, and by the way, I want to know how far across this is. This should be 4 okay, so 4 inches and 3/4. So here's hoping it's 4 inches and 3/4. No, this is not. It needs more, needs to be compressed more. So let's go ahead and, you know, turn this in a bit more. So this, of course, can affect the values as well for these, for that inductance that we had just measured. So just want to make sure this doesn't bam into the stuff and all that. Okay, hopefully this accomplished the goal of 4 3/4 inch. And lo and behold, we exceeded it. So that's excellent. So actually we need to loosen this a little bit. And so let me go ahead. So there's 4 and a little bit more here and here. So 4, we need 4 3/4 inch. And that would allow us to put it in the crate. Let's see here. So there's, yeah, so that's 4 3/4 inch right there. So that's great. Great news. Okay. So here's the other deal. We need to go ahead and hook up some leads here. So here's my leads again. No, wait, that's the wrong one. I need the ones that are not. 4 wire leads over here for my milliohm meter. That's too close. Let's zoom out. So let's go ahead and measure this thing. Almost edging on 7 hours, and I think I could finish the attachment of the fan and stuff, but we could do that tomorrow. Or we could do it when I move back. So here it is. Here, 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 and then this thing goes back to here. Let's go ahead and make our connections over here. And we don't want to induce any voltage when doing the resistance measurement because that interferes with the reading and all. So we just leave it alone and we turn it on. And lo and behold, we have 320 milliohms of resistance, or 0.32 ohms. We cannot show in that setting, so this is the lowest setting that it can be picked up, 0.32 ohms, or 320 milliohms. Okay. Now I had adjusted the coils, I had compressed the coils a little bit, so actually I should get more voltage induced because there's going to be more lines of flux that are capable of crossing, especially on the sides, and that's where I want it to cut, is through the sides. So let's go ahead and take care of that. Now, this current configuration for the S.H.O drive, I'm not 100% confident that this will work, because I might have to take this end here and bend it upwards to reduce the drag here, because the field lines will reverse as you go around to the other side. It will reverse. Now, if I bend this up, it goes like an arch over here, and I'd have the same thing down below if I do that. Doing that means it's only going to reduce, it's not going to reverse, and so it's going to be less of a cogging effect. Now, as this magnet, oh, okay, we'll make sure that's off. Good, okay. We want to be inducing things here. Okay, so when this magnet is rotating up through here, it induces lines of flux through the sides here, but the field gets stronger. It's supposed to get stronger as it gets closer to this edge here. So while it's gonna, let's say this is a north pole in this direction, and it's rotating up, and it rotates up over here, it's gonna induce that north all the way to here, where it might actually be stronger. Now, if I bend this up, then there's a point where it starts to reduce. Like, if I have this bent up, then it's over here, and there's lines of flux coming out and fanning out this way, and it will see it sooner if this is bent up. And so we'll induce the flux while it's here, and then by the time it's over here, since most of the flux has already passed through, it's not going to be as much cogging effect here, as well as the fact that the field's not going to be two opposite directions on opposite sides. So I might have to make that adjustment later, but right now I don't want to mess with that. I want to see if even this thing will work. It might speed up on this section, then slow down, speed up, slow down. I don't know what that balance is yet. So anyway, let's go ahead and measure our inductance again, because we had just changed the shape of the coil. So we'll need to do that. And I do need new leads. Wrong one. Let's see how kind of messed up that one is there. It's no good. But good enough for situations where there's no current of significance going through, such as with resistance measurements and voltage measurements. Yeah, without the current. I mean, you just have a high impedance inside. Yeah, this doesn't go here anymore. Take that out. So since I had done this, we're going to measure the inductance of this. Okay, now we got 0.935 millihenries of inductance, or 935 microhenries. Okay, let me move this chair out of the way. This is obscuring your view. Okay. And this is, of course, not belonging here either. Let's move this chair away. And I think I might just assemble the fan assembly and all that in the tachometer assembly tomorrow, but I don't know if I'll have enough time. Okay, so there it is. What else is new? Oh yeah, the oscilloscope. So let's go ahead and turn this off and disconnect these. And we're going to do our oscilloscope reading. Finally got this done. Why do I have to be a last minute person, huh? I mean, I have to wait till the end of the lease and then I start building the show drive. Well, I had to modify the plans and all that stuff, so that took a while enough. And finally, of course, it's pretty much the end of that. So let me go ahead and hopefully I can go reach this one here. And then over here, pick another reach here. Oh, that's not good. Let me go ahead and take this one here. This one here needs to grab here somehow. Start on again. Alright, hopefully this is a better angle than before. Kind of like messed up the angles over there. Oh. And so let's go ahead and get rid of that screen thing again. Oh, okay. So let's go ahead and let's see what kind of voltage we get now for the induction. So here's 1 volt divisions. 1 volt divisions. So getting positive, the minus 1 volt. Not too bad. So, okay, so let's go ahead and look at our, reduce our divisions or something. For the, there, 0.1 volt division for the vertical axis. Okay, that's going way off the chart, but you see here, it's going off the chart. Let's go ahead and do a little bit less extreme. 0.5 volt divisions, so half volt divisions. Be nice to see the refresh rate would be bigger. So 1, 2, 3, 1, 2, 3, 1, 2, 3. Okay, let's just make sure that this is still the length I want. So yeah, this is still pretty much changes the. It will be. I'll have to glue the ends here eventually. So here is 4 points. So 4 3/4. Perfect. So again, here. Okay, so this should give us RMS voltage on the bottom right. Yeah, I'm definitely have to glue this eventually, or use a stopper of some kind. I need a different method than what I have right now, so. See if there's any average voltage. Should be 0, pretty much. Good. Max. Okay, or how about frequency? Why don't we show frequency? This doesn't really understand the frequency or the waveform, so let's see here. Fit base. How did I do this? .1 second time base, so 0.1 seconds for each division. Okay, so obviously, just kind of like adjusting this. So that's the waveform we're getting. It's not exactly an AC waveform. But you have an idea what you're seeing. See? So there it is. It's like a double hump camel type of waveform, but it's sort of alternating. So mainly because let's say I turn it the other way, I'm just reversing the camel humps on there. So yeah, you can see closer. I'll be very careful before I, do this thing. Now you see, this gives you a graph of where this is at. So 0.5 volt divisions. So this is going up to like 1 volt, and 427 hertz at circles. But 0.1 second division. So let's see. Okay, so this kind of gives us an idea. So in half the screen we have like 3 rotations. So that half the screen, 6 divisions. So we're doing, that was like 0.2 seconds for every rotation. So that was 5 hertz, and so 5 hertz translates into, what are we talking about? 60 seconds, so that is 5 times 60, so that was 300 revolutions a minute. So at 300 revolutions a minute, this would induce, essentially, so it would peak at, you notice how when it was faster, it was higher, and as it slowed down, the peak voltage dropped. So let's go again. It's not connected anymore. Wrong. Okay, so once again, we're too close. Alright, so here again, spinning. Let's do it a little bit better. So here's the waveform again. Okay, 0.5 volt divisions. So here I have a situation where I have essentially 4 or 3 or like what could have been 4 rotations for every. So okay, so this screen has 648 millisecond alright, so 0.1 seconds per division, so 0.6 seconds from here to here, from the middle to the right, but here we have an extra, so here. So basically that was 5 rotations a second, or 0.2 seconds per rotation, and we were getting like what? We were getting about between 1 volt and 1.5 volts. So that's at 300 RPM, or 5 rotations a second. If I were to think about how much current I would have then, that voltage, well, first of all, with the inline resistance, pretty much all the impedance is going to be the inline resistance of the oscilloscope. So that's one thing. But anyway, what are we doing? So the L over R constant, or inductance over resistance constant with the oscilloscope attached, of course, would be pretty low. But we see the voltage, and that's kind of like the point. The voltage, pretty much all the voltage generated is going to be inside across the resistance, because it's going to have the highest fraction of the impedance. So it gives us a good idea of how much voltage will be generated overall between the resistance and the inductive voltage, not just the resistance times current. So between 1 and 1.5 volts at 5 rotations a second. It's a little bit less than I was thinking, but I could add some more magnets on the ends if I wanted to. But that also might affect the cogging or something. We'll see. So let's say 1 volt through there, 3 amps. So this motor would burn up, let's say 20 amps or more, let's say 40 or somewhere between 20 and 40 amps through the wire would essentially burn up the wire. So that needs to be avoided. But that gives us essentially so if we're at 300 RPM, inducing 1 volt, getting like 3 1/3 amps. So if I do 6 times that, that's 1800. But of course, then we have the inductance to work with here. So the inductance being was 900 something microhenries. So you'd have to do the math, and 2 pi times the inductance times the frequency, and that depends on the frequency. And so it's 2 pi is about 6. So it's 6 times, it's a little bit over 6. So take something a little bit over 6 and multiply by something a little bit over like 900, a little under 1,000th. So about 1,000th of 6. It's like 6 thousandths. So 6 thousandths of, say if you took the 2 pi times the inductance, so that'll be around 6 millihenries, but then you have to multiply by the frequency. So then you go from millihenries to, you multiply that by hertz to get your milliohms, and that would be for inductive reactance. So 2 pi, so let's go through 6 millihenries times, let's say 5 hertz. So that would be 30 milliohms of inductive reactance at that speed. So 30 milliohms of inductive reactance at that speed. That's compared to, say, the internal resistance of a 300 milliohms. That's just a regular resistance. So at 5 hertz, we're talking about the inductive reactance of being about 10% of the the electrical resistance of the wire. It would have to spin 10 times faster before it reaches in par with it. So it would pretty much it would indicate to me that we're not going to have like most of the flux that gets induced into the coils gets destroyed simply due to resistance times the current. So that resistance times current is a voltage loss due to the resistance, and that prevents us from accumulating magnetic flux linkage. And the rate change of the magnetic flux linkage is also a voltage, but just that's the voltage associated with the inductive interactions instead of the resistive. So the voltage here going through the coil, if we divide that by the known electrical resistance, should give us more or less the correct answer for how much current there would be under that situation. Now, in the event, let's say we've got this going at 1800 RPM, which is 6 times more than 5 hertz, which would be 30 hertz. So you take the 30 hertz multiplied by the 6 millihenries, so that's 180 millihenries, right? 180 millihenries. Excuse me, 180 milliohms. Excuse me, milliohms. So that would add just over half to the resistance. So like you would have a factor of reduction by 2/3, but by that point, 1800 RPM is pretty fast, right? But if I do that, and let's say if I had induced, let's say it was 1.25 volts through, let's say 1.2 volts through 0.3 ohms. Well, let's just adjust, because it was between 1 volt and 1.5 volts when I was rotating it. Just to show you again what this looks like. It's not connected, is it? Oh, now it is. Okay, there it is. There's a waveform. So yeah, 0.1 second divisions and 0.5 volts of vertical divisions there. So yeah, that's going upwards of 1 to 1.5 volts peak. So we're talking about like 1 volt, yeah, or so. What else? So 1 volt at that speed, that's 6 times the speed, 180 with 1800 RPM. So 6 multiplied by 2/3. It's 12 over 3, which is 4. So, because it's 2/3 again, because if you increase the speed, you got the inductive reactance, so that increases in that case. 30 hertz would be 1.5 times the whatever, an additional 180 milliohms on top of the 300. So you'd have 4 times that current. So if it had 1 volt through the 300 milliohms, so that would be like 3 1/3 amps. Multiply that by 4, you're doing upwards of past 13 amps or so, which is acceptable. It would not burn up the wire, so I wouldn't be concerned about that. But it does. That would constitute significant force on the magnet, and I would like to see how it turns out. But I have to sleep, so tomorrow I'm gonna go ahead and finish off this. I'm gonna have to, glue these ends over here on the sides. All right, and then I'll glue it on one side at least, or I could do the rubber band thing where I put a rubber band on this end, so at least I'm not stuck with the glue or wherever it was. So yeah, I can do that. I'm gonna finish the crates, assemble them, and put the fan on this end over here. The tachometer assembly, so I can measure the RPM, and hopefully it works. Now, if it doesn't, I hypothesize then that I need to bend these outer regions down there and up here. So here's hoping I do that. Let's see here. I want to go ahead. Now, I have to leave before 4 o'clock in the afternoon tomorrow, because that's when the lease officially ends, and I have to have everything cleared out. So, and I also do have to move a couple of other things on top of that. I do have a lot of that in the car already, but I would have to do 2 round trips. I'd have to leave in the morning. Let's see here. I'm going to do that as early as possible, and then sort of last minute stuff I would do the recording, but the computer and everything's got to go out the room before, say, 3 o'clock. So that way I can move the bed back to where it was and everything else, and clean the floor, put everything away, not leave anything behind. So yeah, okay. So all right, so let's go ahead and check the time. It's 12:06 p.m. Wednesday, August 31st. It's been 7 hours and 16 minutes. I would like to thank you for your time and have a wonderful day. Oh, of course, I want to take some pictures of the assembly, so let's go ahead and do that. splash it now.
Vertical.
Okay. All right. And just to give you an idea of what the trail camera does. Let's see here. So, all right, let's go ahead and take care of this. So all this time, it's been taking some pictures. Sometimes it takes a picture when I knock it. But anyways, it's been taking a lot of pictures. This little bit pointed a little bit high. But that's because it was adjusted for the workbench, which was a little bit higher. That's fine. So when I have it on the workbench, so you can see it at that angle very well. Okay, that's a little bit better. Okay. So loads of pictures that should help with displaying, you know, the idea of what I'm doing and making and all that stuff. Usually it's used for wild game or, you know, thugs on the street or something. So this is something a little different to use a camera like this for. This is the Crenova trail camera. I can show you the box. As you can see on the box, it gives you some information, 12 megapixel, etc., etc. You know, get the drift. Here
And I got it from Amazon. There's some details for you. So yeah, and so just clicking around, assembling the coil. It gives you the time, the temperature. Yeah, so cool, right? So that's the drift of that, all right? What else could I say? Let's go ahead and turn this off. I always have something else to say before I actually turn off the camera. Alright, so yeah, I can show you the crate once more. You can see here on the inside these rods that we use to hold this in place. This has the correct width that I wanted. Let's see here. So yeah, exactly 4 3/4 inch, which is perfect. It is what I want, and it doesn't bang the side or anything. Or if it does, it's the hooks, which is great. So yeah, let's go ahead and show you a little bit of the inside to get closer into it. So this would be the front end over here. That was really stupid, but thank goodness it's all the way together. There we go. Let's turn this off. So here's the deal. So there's the magnet there. In the middle, you can see that. There's that wire on the front that connects the ends. There's lots of stuff. The hooks are in there holding the coils in place, separated, and it's like that. So super clear. You can hardly hide any batteries whatsoever. This is going to be the real deal if it works. If not, it's an interesting ornament, expensive ornament. The magnets themselves are like $200. Coils, I overpaid. I could have bought bulk and real cheap, but I bought them pre-cut and pre-measured, so it's like they were, to buy both of them was $70 at the price I purchased them at. So that's $35 each. But yeah, the acrylic panels, those were pretty thick, and so those were like $20 for that square foot of a panel. Then maker space was like $70 to get the holes cut through CO2 laser, which was really convenient but also expensive. The shaft is like $1 or whatever. The nuts are like the same, it's like nothing. The Gardner Better stuff, just a couple bucks. That's the here, Gardner Bender ring terminals, just a couple bucks. So just take the most expensive items. Well, the magnets, I mean, that's pretty much by necessity. That's the most expensive part. And the coils you could probably do for like less than half of what I paid. I mean, you could probably do it for like $10 or less. So if you add up the essentials, essentially it's like $250. Just for that. Of course, the crate it's an expensive way to hold the whole thing. And the fan, of course, is something you attach to it. It's not the motor itself. So that would be that fan was like what, like $50 or something. So that's the over here flex fans. So I had that box over there, flex fans, you see. But yeah. So that is all. I would like to thank you for your time. Of course, almost nobody's going to watch the whole thing straight through, so you gotta have like popcorn and invite your friends or something and enjoy the like whole like long session or something. or you could just view the videos, and of course there'll be digests that will basically cut down to the nitty-gritty of what I'm doing. So yeah, so it's the finale of this whole place. I'll have to go back, but at least I've got the basic idea down. I've got it built, and if it doesn't work, I still have some ways to figure out, you know, what to tweak, the shape of the coil, what it needs to be. You know, if I need to substitute the magnet assembly, I could probably redo the magnet assembly at some point, but right now I'm not really into that right now, so it should be okay. Yeah. All right, cool. All right. Thank you, and have a great day.